All right, so here we go, guys. The date today is the holy smokes, 29th. The topic for your notes today is obviously on the board. And guys, as you're getting settled, and again, you need your periodic tables readily available, guys. Get them out of your notebooks. You're going to be flipping them back and forth all over the place today. Guys, but let me help you make sense of what we're doing today, given what we've done. So 2 times ago in class and last time during the lab, you got, hopefully, a pretty good understanding of how this periodic table is put together. You understand the metals are on the left, you understand the nonmetals are on the right, you understand that the metals are big and fat and weak and give away electrons. You understand that the metals are small and strong and they take in electrons, and you're starting to get the idea that this giving and taking of electrons is what atoms do when they form bonds. Well, guys, that's what we're going to talk about today, is what happens when these atoms get together in groups and they form bonds. So to do this, first thing I'm going to do is I'm going to anchor this to what you already know. Then, guys, the next slide is just going to be some terms and concepts you need to write down. And then, guys, we're going to look at the 3 types of bondings that exist in our world, and then we're going to summarize and call it a day. Here we go. All right, so guys, getting started, don't write this down, but I'm curious to know if you remember. So when was the first time in this class you encountered the concept of bonding? Do you remember? Do you remember this? Oh yeah, the kinder, gentler days of chemistry. And guys, down here at the very tippy bottom, we talked about the idea that there are heterogeneous mixtures, there are homogeneous mixtures, and then there are substances, of which there are 2. There are elements and there are compounds. And guys, we define compounds as being 2 or more elements bonded together. Is this coming back to you? Okay, but guys, the trick is between then and now, you guys have learned all sorts of stuff about elements that we can talk about. So the thing that you need to understand about elements is that fundamentally there are 2 types. There are metals and there are nonmetals, right? The elements on the periodic table can be broken into metals and they can be broken into nonmetals. And that's going to be important because what you're going to find out today is that when they bond together, these metals and nonmetals form compounds. And what you're going to find out is there's only 3 different types of compounds. So sometimes when elements bond together, they form compounds which we call salts, which is this, right? So table salt. But guys, the trick is table salt is not the only kind of salt. There's actually thousands of different salts, of which NaCl is simply one of them. So sometimes when things bond together, they form salts. But that's not the end of the story. Sometimes when they bond together, they form things called molecules, like water. So we're going to talk about what is the difference between the bonding in salt and the bonding in water. But there's actually a third thing that they can do. There's a third type of compound, and these are called the metallic compounds, and that would be that guy. So guys, this is our outline for today. We're going to talk about what is going on inside of salt, what is going on inside of molecules like water, what is going on inside of metals, and when we're done with that, we're going to summarize and call it a day. You ready to go? Okay, so terminology first. Draw Mickey Mouse taking a nap. So guys, but seriously, make the big circle, 4 centimeters, 2 inches across? And then make the small circles, 2 centimeters, maybe an inch across? I do, but it won't help you draw circles. But guys, you understand, and maybe some of you know, what molecule is this? It's water. This is what a water molecule looks like. You're going to find out later in the unit that the angle that's formed between the hydrogens and the oxygens actually, 104.5 degrees, yeah. Yeah, you bet. I probably shouldn't throw this, but there you go. That wasn't bad. Okay. So guys, make this big enough that you can label it, because when we talk about bonding, we need to talk about some terminology, and it's all going to go in Mickey Mouse. So draw this big enough that you can write some things inside the circles. You guys done? You're good? Okay. So guys, the first thing you need to do is this. Draw lines that connect the nuclei. And these lines that you just drew actually have a name. They are what are called bond axes. So you could just label one of them bond axis, or you could label them both, because they're both bond axes. Guys, you'll notice, though, that we did not connect the two hydrogens, the little guys. You'll notice we didn't connect them with a line. Why not? They're not bonded to each other. These are both bonded to the oxygen, but the hydrogens aren't bonded together, so they don't have a bond axis because no bond exists in between these. So then, guys, drawing on your geometry background, you can see that the point where these meet, well, the place where these lines meet creates an arc or an angle. And guys, this angle we call a bond angle. And again, you're going to learn the bond angles for these molecules. It's not hard. This is actually about 104.5 degrees. You'll be good. Okay, so now guys, the next one is hard to see. So are you all caught up? Are you okay? So guys, blue doesn't stand out very well against black. I probably should have chose a different color. But guys, if you look right here, draw that distance, like draw that double-headed arrow indicating that distance. That distance between the nucleus and the valence electrons. Gosh, that sounds familiar. Yeah, it's the atomic, but guys, don't label it atomic radius because it's actually no longer the atomic radius. You know the distance between the nucleus and the valence electrons is the radius, right? But now this atom is bonded to another atom, so it's no longer the atomic radius because the atom's not by itself. This is actually what's called the covalent radius. And guys, if you grab your periodic tables, you'll notice that this data is given as well. It's actually, is it the top number? Yeah, so it's the top number in the pink box in the upper left-hand corner on the back. The top number, pink box, upper left-hand corner. But guys, you'll notice that the atomic radii and the covalent radii for these atoms are not the same. The reason is because these atoms squish or stretch when they bond to other atoms. Some of them get smaller, so the covalent radius is smaller than the atomic. Some of them stretch out, so the covalent is bigger than the atomic. But in either case, you need to say they're not the same. So we need to know the covalent radii. The reason we need to know the covalent radii is because of this. Guys, watch right here. Now draw a line that connects the two nuclei. We're almost done with terminology. So guys, that distance between the two nuclei actually, of course, has a name as well. It's called the bond length. And one of the things that you've got to be able to do using your periodic table is calculate bond lengths. How do you do it? Exactly. Add up the covalent radii. See guys, this distance right here is the covalent radii for oxygen. That distance right there is the covalent radii for hydrogen. You add those up and you get the complete bond length, which is the sum of those two radii. So guys, if that doesn't make sense, we write that like this. Remember the sexy E is actually the Greek letter sigma, which means sum, which means to add together. So the covalent radii, the bond length is the sum of the covalent radii. That makes sense. So guys, there you have it. That's all the terminology you need to know. You need to know that these are called bond axes. You need to know that they form a bond angle. You need to know the covalent radii. You need to know that the covalent radii add up to bond length. Yep. Well, so because for some, and this actually, we're not going to get into this, but the reason is because of electronegativity. So highly electronegative atoms like oxygen, they will actually compress when they covalently bond. They actually get a little bit smaller. Weaker atoms like hydrogen will actually extend when they covalently bond. And so what you'll find is that when an atom gets involved in bonding, it deforms a little bit, and that's why there's a difference between the two. You guys good? You all caught up on terminology? You ready to start thinking about bonding a little bit? Okay, so guys, these are then the transitional thoughts that you need to understand in order to understand this idea of bonding. So first of all, what are chemical bonds? Just write down the definition, and then we're going to talk about it. So a chemical bond is or are attractive forces that exist between atoms, holding them together to form compounds. So atoms bond together. That could be NaCl, that could be H2O, that could be CO2. When atoms bond together, they form compounds. And these bonds are just attractive forces that hold them together. Now, guys, the question is this: what part of an atom forms the bond? Do you know? I think you know. When atoms form, when bonds form between atoms, physically, what part of the atom is interacting to form the bond? The electrons. Guys, electrons form bonds, which brings us to this point. These attractive forces are created when valence electron clouds from two atoms interact with each other. So when these orbitals, these clouds, however you think about them, when these clouds interact, the electrons actually form attractive forces, which we call bonds. So guys, when you're done writing this down, you're done taking notes on this page, because everything else that's going to come up just sets the stage for what we're going to do for the rest of the day. So here's what we know. Bonds are attractive forces that hold atoms together to form compounds. We talked a second ago about there's three kinds of compounds. There's salts, there's molecules, and there are metallic compounds. What we're going to talk about to round out the day is what is the difference between the bonding in salts, the bonding in molecules, and the bonding in metallic substances. And guys, in order to figure that out, I'm going to sort of set the stage for you right here. Then we're going to dig into them one at a time, and at the tail end we'll summarize. You ready to go? Okay, so guys, don't write this down. Just trust me, it's conversational. So the idea is this. There are different types of bonds that can be formed, and the type of bond that forms depends upon the characteristics of the atoms. So the idea is, we know that there's two different kinds of atoms. There are metals and there are nonmetals. So this is the conversation we're going to have. What happens when a metal bonds to a nonmetal? Then, what happens when a nonmetal bonds to a nonmetal? And then, what happens when a metal bonds with a metal? And what you're going to find out, because we've got metals and nonmetals, there's three different pairings. We can go metal to nonmetal, we can go nonmetal to nonmetal, and we can go metal to metal. And the different pairings determine the type of bonds, which then determines the type of substance, whether it's a salt or a molecule or a metallic substance. So guys, this is what we're going to do for the rest of the day. We got three things to talk about. You ready to dig in? Here we go. So guys, first of all, metal to nonmetal, right? That you got to get. So metal to nonmetal. And you'll be glad to know I did more animations. Now I know that the electronegativity animation was sort of the summit, the peak. I've got another one that's not bad too. All right, so guys, maybe up to you. Let's talk. So we're now talking about a metal bonding to a non-metal, and we're going to start out by asking some questions. If you want to write them down, okay, but I don't know you need to, because what if we talk about this? What are the chemical properties of metals? So, right, and you guys are going to get sick of me asking these questions, but that's okay. So guys, where are the metals on the periodic table, the left or the right? The left. Are they big or small? Big. If they're big, are they strong or weak? They are weak. And if they're weak, what are they going to do with electrons? Take them in or give them away? Good. Okay. So metals on the left are big and fat and weak electron givers. Can I get an amen? All right. Now, because you all know that amen just means we agree, right? All right, just checking. Okay, so now guys on the right, let's now talk about the nonmetals. So the nonmetals are on the right, so are they big or small? Small. So are they strong or weak? Strong. So do they take or do they give? They're takers. So guys, the question then is this: what's going to happen when they get together? When you've got a big fat metal that is an electron loser and a small strong nonmetal that is an electron taker, what is going to happen when they get together? The metal is going to get his butt kicked, and he's going to end up giving away his electrons to the nonmetal. But guys, when a metal loses electrons, what happens to it? It takes on a charge. What charge? Positive or negative? Positive. And what's going to happen to the nonmetal when it steals the electrons? It becomes negative. And what do positives and negatives do? They attract. And that's what happens. And there's a name for it. It's called ionic bonding. So guys, when you get a metal together with a nonmetal, you end up with what is called ionic bonding. And here's how this goes down. So guys, an ionic bond happens when a strong nonmetal steals electrons from a weak metal. And when this happens, ions are formed, right? The metal loses electrons, it becomes positive. The nonmetal gains electrons, it becomes negative. That's why we call it ionic bonding. Hi, Tilly. How are you? But guys, what do positives and negatives do? They attract. So guys, these ions then attract each other, bond together, and form salt. So now you're saying, wait, every single combination of a metal and a nonmetal forms salt? Yeah. But you got to understand that sodium chloride, which you call salt, is not the only salt. Guys, there are thousands of different salts, of which sodium chloride is the one that we eat most frequently. So we just call it salt. But guys, anytime you've got a metal and a nonmetal, you've got a salt. So let me show you another example. Can I show you another example? Is that okay? Oh, this is like medium animation skills. So, guys, first of all, what is a salt? It is a compound that contains ionic bonds. So what does that look like? Well, I'll let you write this down so you can see. So that is actually the definition of a salt, a compound that contains ionic bonds. So what does it look like? Well, guys, let's take, and again, don't write this down because you can't do this. So, guys, let's take the salt, the metal lithium. So lithium is element number 3. It's over on the left. It's definitely a metal, and it's like so. Now, guys, let's grab the nonmetal fluorine. So, guys, fluorine is element number 9. What do you know about fluorine? It's the most electronegative element on the periodic table. Guys, fluorine's scary stuff. It rips electrons off of everything. So what is going to happen when a lithium atom and a fluorine atom get together? What's the fluorine going to do to the lithium? Steal its electrons. Ready for this? Here it goes. So lithium is going to lose its Oh yeah, lithium is going to lose its electron to fluorine. And when it does, what does that do to the lithium atom? Makes it positive. What does that do to the fluorine atom? Makes it negative. And guys, this positive and negative then attract together, and we end up with a salt called lithium fluoride. Huh? And guys, that is what happens in all metal-nonmetal pairings. The nonmetal steals electrons from the metal. It makes the nonmetal negative, the metal positive. They attract, and it forms a salt, in this case, lithium fluoride. Yeah?
So what is formed of greater electronegativity than neon?
Well, so neon should be more electronegative. The problem is neon doesn't have anywhere to put its electrons because it's got a full shell. Yeah, so really, the most electronegative element on the periodic table should be helium. It's just that helium has nowhere to put the electrons, and therefore it can't steal. Is that okay? So guys, questions on ionic bonding. We've got a metal, we've got a non-metal, we've got stealing, we've got ions, we've got attraction. That makes salts. Salt is one of the 3 types of compounds that we talked about, so these are salts. You guys good? Okay, so now let's look at the next atom pairing, which is non-metal, non-metal. Write that in your notes. This is going a lot better than I thought it would. I figured by now I would just be coughing and hacking, and thank goodness for Dayquil. Better living through chemistry. Right now there are all these little molecules from those drugs floating. See, it's molecules, it's chemistry. Okay, so guys, same questions. Let's try this. So, when we talk about nonmetals, are they on the left or the right? They're nonmetals. They're on the right. So are they big or small? Small. Are they strong or weak? Strong. So what do they want to do to electrons? Hang on to them. So guys, the chemical properties of nonmetals, they are small, they are strong, they are electron stealers. Now, guys, what is going to happen if you get 2 nonmetals together? They're going to try to steal each other's electrons, right? But what's going to happen if you get 2 stealers together? Guys, I've got a great analogy. It's not even an analogy. This is the way it works. Have any of you ever worked in the nurseries at your churches? And you know that if you walk into that nursery, about 18 months to 2 years, those little kids learn the most important word they will ever learn in their lives. It's not mommy, it's not daddy, it's mine, right? You know what I'm talking about. You walk into that nursery and you know the kid that figured out mine, because that kid is surrounded in toys, right? He has stolen everybody's toys, and he just sits, he's very electronegative, and he just sits there, seriously, and he protects those toys, right? But have you ever seen this go down where there's this other little kid that decides, I'm going to go get me one of those toys, right? And that kid that's surrounded in toys can be playing with whatever toy he's playing with, but if somebody touches that toy over there, all of a sudden that becomes the most important toy to this kid, and he drops whatever he's got and he latches onto that, right? Okay, now you know the way this goes down. If the kid that comes to steal the toy is weak, that kid's going to end up getting thumped and he's not going to get the toy. But guys, what happens if you've got this greedy kid with this toy? I've actually done this in nursery to see if it works. Hi. What's going to happen if you've got this really greedy kid in nursery and this other kid comes over to grab a hold of the toy, and now they're both latched onto the toy, but the kid that came to get the toy is not going to let go because he's pretty strong too. What's going to happen? I've actually done this. If you take either one of those kids and pick them up, guess what? You get both the kids, because they're both latched onto the toy and neither one will let go. Seriously, try it when it's Sunday. Try this. You grab this kid and pick that kid up, and the other kid comes up off the ground. Because literally they are bonded together. They are both latched onto that toy and neither one will let go, and as a result they are quite literally stuck together, right? Well guys, atoms do exactly the same thing. If they both latch on to the same electrons, and if both of them are small and strong, nonmetals, neither one of them will win and neither one of them loses, and they are quite literally like 2 kids in a toy latched together. Guys, the same thing happens here. And that is what is called a covalent bond. Now, don't write this down. We're going to talk about this. But guys, this can happen in one of 2 ways. This can happen equally. If both of these kids have the same strength, they will actually share equally. But if one of the kids is a little bit stronger than the other, then they will share unequally. And we give names to both of those. So the weird part about this in the world of atoms is when we talk about sharing, what we're really talking about is this greedy hanging on to stuff and they won't let go. Sharing sounds actually kind of nice, right? Like I'm sharing with you. No, they're not. What they're actually doing is fighting over electrons, and neither one of them wins and neither one of them loses, so they end up sharing. But it's not like they're being kind. It's actually they're both being greedy. So, guys, we call all of this covalent bonding, and this is where you need to get going with your notes again. Oh, gosh. What? So I'm actually not. I'm not LDS. So I attend a church down by Walmart, down by UVU. It's called Centerpoint Church. Yeah, you should. Oh my gosh. Like, on any given Sunday, we have 100 to 200 kids in our nursery. It's unbelievable. It's crazy. I mean, we've gotten to the point where we do electronic check-in and check-out in barcode kids. Yeah, it's nuts. Okay, so guys, covalent bonding. Covalent bonding are the bonds that are formed by the sharing of valence electrons. Now, guys, we sort of touched on this idea. We're going to go a little deeper into this. So this sharing can happen in one of two ways. If you've got two atoms that have the same strength, they will share equally. If you've got two atoms that don't have the same strength, they will share, but not equally. It'll be lopsided. And we have names for those. First of all, equal sharing. Equal sharing is what is called nonpolar covalent bonding. Guys, that would be a word to underline. That guy's important. Nonpolar covalent bonding. You know what? I'm going to underline it too. I can do that. Here we go. Okay. So guys, here's the question. It's kind of a weird question, but try this on. Nonpolar covalent bonding is perfectly equal sharing. So the question is this: what two atoms would be able to share perfectly equally? They'd have to have exactly the same strength. So guys, which two atoms would have exactly the same strength? Two of the same atom, right? And guys, that's the idea, that this occurs when you have two atoms of the same nonmetal. And when this happens, you get equal sharing and what we call nonpolar molecules. So guys, this doesn't form salts, this forms molecules. Just go when you need to, but you won't make it back in the time for class, so just watch the screencast to catch the rest. Although we may be done. So guys, can I show you a picture? I know this seems a little fuzzy, but let me show you. You ready? Okay, so understand this only happens with the nonmetals, right? We need two atoms that are strong enough that they both can really hold on to electrons. So guys, let's take a fluorine atom and then let's bring in another fluorine atom. So here we've got fluorine with 7 valence electrons. Here we got fluorine with 7 valence electrons. They are both really, really strong nonmetals. These are like the kids in the nursery. And they come together and they start tugging over these electrons. And this is the way this goes down. One of these fluorines reaches over to the other fluorine and goes, mine. And then this fluorine reaches over to this fluorine and goes, mine. And they're tugging on electrons like kids tugging on toys. But guys, these guys have exactly the same amount of tug. And as they both start pulling on the electrons, that pulls them closer together. But as they come closer together, you'll notice that these electrons are exactly between the two of them because they have the same strength. And as a result, we form a compound called nonpolar fluorine. It's actually difluoride. It's a nonpolar difluoride molecule. because you've got two fluorine atoms attracted to each other. And this is a nonpolar difluoride atom because neither one can steal, so they end up sharing, but they share equally because they're the same atom. Is that okay? So now, guys, let's look at this when we have two atoms that aren't the same. And this is what is called polar covalent bonding. This should go in your notes as well. You know what? I'd like to underline this as well, maybe. This is another important one. All right, so guys, polar covalent bonding. This happens when you've got different nonmetals. So they're both nonmetals, so they're both strong. But they're not the same nonmetal, so they're not equally strong. So what's going to happen when you get two different nonmetals that start pulling on electrons? Or are they going to share? Yeah, because neither one's strong enough to win. But they aren't going to share equally. They are going to share unequally. And guys, this creates something called dipoles. So here's what we're going to do. I'm going to define dipole for you, and then we're going to forget about it. It's not going to be on the test. You don't need to worry about it. I'm presenting the idea to you now, so when we get back after Christmas, I can say the word dipole, and you're going to go, ooh, I've heard of those. You will have forgotten, but at least you will have seen it before. So we have a little bit of common ground. So guys, what are dipoles? Dipoles are partial charges on bonds created by unequal sharing. Write it down and then pretend you never saw it. We're almost done. Well, after the review. Bless you. Did you get this thing too? It's cold. No, I hope not too. It starts with a little sore throat. Did you get it? Yeah. Yeah. So guys, when this happens, this forms what are called polar molecules. So I'm going to show you a picture, an animation. Did you guys like the nursery analogy earlier? Not bad, right? You've all seen it. Mine. Good night. Okay, so guys, let me show you an animation of this one then. So, what we're now talking about are molecules that are formed by nonmetals. So they're both strong, but now they're not the same nonmetal, so one's a little bit stronger than the other. So let's now do this. Let's trade our fluorine for an oxygen. So now we've got an oxygen over here and a fluorine over here. Let me do the lights for just a second. Guys, which one is stronger, fluorine or oxygen? How do you know fluorine? To the right. Yeah, right? Because as we move to the right, they get stronger. So fluorine will be stronger than oxygen. But oxygen is still strong enough that fluorine can't steal from it. So now we're going to end up with lopsided sharing. So what does that look like? Well, guys, the oxygen reaches out, or I'm sorry, the fluorine reaches out to the oxygen and says, mine. And then the oxygen reaches out to the fluorine and says, mine. And now they're tugging on each other's electrons. But why are the electrons closer to the fluorine than the oxygen? Because the fluorine's stronger. It's kind of like that kid that pulls on the toy and can get the toy closer to itself because he's a little stronger than the kid that's fighting for the toy. So now when these atoms close down on this, the fluorine gets really close and the oxygen ends up a little farther away because the fluorine's negative. Now this bond is not balanced. It's lopsided. We call that polar. And guys, the idea then is that this creates dipoles. Because these electrons are negative, this is the negative dipole, this is the positive dipole. Don't worry about that. We'll talk about it in the next unit. You just need to know unequal sharing, lopsided bonding, we call it polar. You good? All right. So guys, what's left? Look at what we've done. We did metal to nonmetal. That forms salts. Now we've done nonmetal to nonmetal. That forms molecules, either polar or nonpolar. So guys, what's the only other combination we haven't done? Metal to metal. So let's do that now. So guys, a metal with a metal. A metal with a metal. Ooh. Good. So no, not immediately. We could talk about alloys, but the trick is with alloys, you actually put other elements inside there. Sometimes it's other metals, sometimes it's carbon, to make alloys. This is not alloys. But what I'm about to show you, if you could pull out some of these atoms and stick other elements in there, then it would be an alloy. Yeah, that's cool you know about that. So guys, let's talk about metals. Are they on the left or the right? You're getting sick of this, right? Left or right? Left, big or small? Big, weak or strong? Weak, take or give electrons? Give them away. So guys, the question is this. What's going to happen when you get a bunch of big, fat, weak metal atoms together? What are they going to do? Yeah, they're all going to give their electrons away. Can you picture this? A bunch of big, fat metal atoms going, here's my electrons. I don't want them. You take them. I don't. And who's going to take the electrons? Nobody. Because there aren't any nonmetals there. Inside of a metal, it's all just metals. And all these metal atoms are just dumping their electrons, and nobody's there to clean them up. So where do they end up? In a puddle. Guys, quite literally in a puddle. And we give that puddle a name, but let's make sure you understand what we're talking about. So the idea is this. These are metal atoms. These are actually lithium atoms. And guys, all of these lithium atoms are big, fat metal atoms, and they've all got these electrons in them. Well, I don't want them, you take them, you take them, I don't want them, you take them. And guys, literally, check it out. Literally, they all just start dumping their electrons. And where do they go? Well, they've got nowhere to go. So where do they go? They end up in between the atoms. They're literally just floating around inside of there. But guys, what's the charge of these electrons? Negative. And what did the charge of these atoms become when they lost their electrons? Positive. So now all of these atoms are positive, and all these positive metal ions, check this out, are floating around, in a sea of electrons. And that's literally what we call this. It is a sea of electrons. And what's going to happen between the positive ions in this sea of electrons? They're attracted. And guys, that's what makes metals metals. So guys, everything that you know to be true about metals is all because of this sea of electrons. So guys, what about this? Why are metals shiny? Because light bounces off the sea of electrons. Why do metals bend and not break? Because all you're doing is smearing the sea of electrons. Why is it when you hit a metal, it smushes and doesn't shatter? Because all you're doing is smushing the sea of electrons. Why do metals conduct electricity? Because all electricity is a flow of electrons, and if you put electrons in this end, they just flow through the sea and come out the other end. Guys, everything that you know to be true about metals is because inside metals, literally, there are these metal nuclei just swimming around in a sea of electrons. Do you get the idea? So we actually use that term. This is what is called the sea of electrons. This is actually the image that comes out of my AP book. I like mine better because it looked like a sea. But guys, literally, this is what it looks like inside of a metal. You've got these metal ions all attracted to this sea of electrons. So in metal with metal, just write down sea of electrons and you're good. David, you're going to make it. So guys, what I'd like to do is this, and it's completely up to you. If you feel like you've got a good handle on this, maybe you don't need to do this. Maybe if you want to just go home and print the notes, you could get this. But typically at this point, it's good to summarize. So guys, if you want to do the summary with me, draw this grid. Make it as wide as your page and make each horizontal row 3 lines tall. Actually 4. 4 lines tall. And guys, what we're going to do is we're going to summarize everything that we just talked about. Again, this is not new, it's all review. So guys, as you're writing this down, I forgot to mention to you two things. Your extra credit is recorded. The way that I did this is, Miss Collin, I decided to make your extra credit worth 1.5 grade points. Actually, that's not true. Two grade points, sorry. And so that ended up being 15 extra credit points. So what you'll see in the grade book is the very first assignment of the quarter was a 0-point assignment called extra credit. So if you did the assignment and met the requirements, you got 15 out of 15. If you did the assignment but didn't meet the requirements, like you didn't do all of the sub-levels, I gave you partial credit. And then for a couple of you, because frankly you just knocked it out of the park and what you built was really cool, I gave you 20 extra credit points, which is extra credit, which frankly only happens at places like Orem High. So anyway, and then the other thing I wanted to mention to you was, guys, if you did the remediation test for the nuclear chem unit, those are graded and recorded, and I'm happy to share them with you. Okay, so guys, this is what we're going to do. We are going to talk about the types of bonds, how they form, or I'm sorry, what atom pairs form them, how they form, and then what those substances are like. And then, of course, we've got ionic, covalent, and metallic. Then, guys, if any of you need homework packets, because you weren't here to get those last time, I've got a few, well, 2 times ago. I've got some there. So guys, I'm going to try to do this questioning rather than telling, because you should know the answers to these. So when we talk about ionic stealing bonds, guys, what atom pairing forms an ionic bond? A metal, which is big and fat and weak, and a nonmetal, which is small and strong. So it's a metal and a nonmetal. So guys, how do these bonds form? Well, the nonmetal steals an electron from the metal. That forms ions, and they attract. So we say it this way. Electron transfer, creating ions, which attract. And this forms what we call salts. Examples are things like sodium chloride, which you know, calcium iodide, lithium fluoride, which we showed as the example. Any metal with a nonmetal is a salt. Guess what you're going to learn to do in the next unit? Name them all. Brushing your teeth will never be the same again. You'll turn the toothpaste tube over and go, I know what all this stuff is. Sodium fluoride. So guys, these are the things that you need to know about the salts. They contain ions, they're solids, don't conduct electricity, but their solids are really hard to melt. If you don't believe me, go home tonight, get a saucepan, throw table salt in there and put it on the stove. You can't get it to melt. Table salt, all salts, have ridiculously high melting points. Hot enough that you can't get there at home. You can get there, just not at home. You guys good there? So now let's talk about covalent bonds, sharing bonds. So guys, if we're going to create a sharing bond, what atom pairings make those? nonmetal to nonmetal. If they are the same nonmetal, it's a nonpolar bond. If they are different nonmetals, it's a polar bond. So how do these bonds form? Well, they form by the sharing of electrons. This forms molecules, carbon dioxide, water, and all the biologic molecules, the sugars, the fats, the proteins, DNA, RNA, enzymes. All of those are molecules. They can contain sharing covalent bonds. And then, guys, for the nonmetals, or I'm sorry, the molecules, you need to know that they don't contain ions, so they don't conduct. They have low melting points. Try putting sugar on your stove at home. Sugar will melt, salt won't. Water is already melted. That's why it's a liquid. And they insulate in all phases. You can't get molecules to conduct electricity. Water doesn't conduct electricity. Yeah, so like if you're in a swimming pool, you know, like if you're in Sierra Pool and a storm blows in, there's actually no safer place to be than in a pool of water. The problem isn't the water, the problem is all the stuff that's dissolved in the water. They put chlorine in there to purify it, kids pee in there, everything else, and it's all that stuff that conducts the electricity. If you were in a pool of just water, you'd be completely insulated from lightning. Yeah, unless it hit the ground and traveled through the ground. So if you were floating in a lake of water, just water, and lightning hit the lake, you'd be fine. The problem is the stuff that's in there. You guys good? Okay, so now let's do metallic bonds. Guys, metallic bonds, no surprise, formed by metals. This is a delocalized, which means without location, spread out, sea of electrons around weak nuclei. And these things, as we said, conduct. They are ductile, which means they stretch. They are malleable, which means they smush. They are shiny, and they're really hard to melt. See that? And guys, all of those things is because of that sea of electrons. So that's what you need to know. Oh, cool. Guys, we got 15 minutes. I think you may get your homework done.